Good morning to all of you. Hello, am I audible?
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. So, are there any questions, doubts? Hello, anybody? Any question, doubt you want to ask? See, in the Impartus, the videos of the lectures are uploaded, and also the PDF of the whatever I am writing, the PDF files are also available under Backpack. So, under lectures, you can see videos, and under Backpack, you can see the PDFs of the lectures. So actually, you should go through the content, whatever I teach, and clarify the doubts whatever you have. And today attendance is only 12 people. I think I'll have to tell then, uh, Commander. YCNCW, I'll have to tell that students have there is a poor attendance. I think please tell your other friends that they should all attend the class and in time. Otherwise, I'll have to report it to ICNCW. Okay, so if there are no questions, let me start. So, is my screen visible?
Yes, sir, it's visible.
Yeah, I had closed the my file, this window journal file. So, is it visible now?
Yes, sir, visible, sir. Right.
Okay. So, yeah, then let me start. So, we were discussing this approximate analytical solutions. So I had discussed Galerkin method, Petro-Galerkin least square point collocation. So the last weighted residual method which was left was the known as the fifth one, and that is known as subdomain collocation. So one was point collocation, simply referred to as collocation method, where residual is equated to 0 at selected points and the number of points are equal to the number of unknown constants in the approximate solution. So I had demonstrated you that. So the last one under that is what is known as subdomain collocation. So in this, as the name suggests, it is a collocation method but subdomain. So rather than a point, it is a part of no subdomain means domain means the entire domain over which no the differential equation is defined, or the domain of interest. and then in that we divide into some smaller subdomains and equate the residual integral equal to 0 at those in those subdomains. So that is known as subdomain calculation method. So in this case what we do is set integral of residual equal to 0 at each subdomain. And how do we decide the number of subdomains? So that depends on the number of unknown constants. So number of subdomains is equal to the number of unknown constants in the approximate solution. So this is obviously after number of unknown constant means after we satisfy the boundary conditions. So number of unknown constants in the approximate solution. So like if you the problem we were continuing, so the beam problem, and where we have assumed the solution as no constant a1 into sine pi x by l. So for that problem there is only one unknown constant, and the domain is we had this x, and this is origin, so x equal to 0 there, and here it was L, the total length. So we need to choose only one subdomain. So the subdomain can be the entire domain itself in this case, because we want to choose only one, or it can be part of this. So suppose we choose part of that as the subdomain, so this one, so then this will be subdomain, this portion. So this is say we choose this as the subdomain in this case. So then what we will do, the subdomain is governed by two boundaries. So say this is x1 and this is x2. So let us say we choose this is arbitrary, that we can choose any no anywhere this domain. So say x1 is L by 4 and x2 is 3L by 4. So we choose the central half of the domain is the subdomain for the subdomain collocation, and then we set the integral of residual equal to 0. So the integral of residual x1 to x2 rd dx is equal to 0. So now x1 is L by 4 and x2 is 3L by 4, and the residual we had calculated as pi by 4, pi power 4 upon L power 4 into ei into a1 sine of pi x by L minus q. So this was the residual. I know if you remember last class, right? So it's the same thing, dx is equal to 0. So now if you perform the integration, so the first term the integral will be the integral of the first term, and that is pi power 4 upon L power 4 into a1 into ei, and the integral would be minus L upon pi cos of pi x by L. The limits are L by 4 to 3L by 4 minus q, and that is the integral simply x, and the limits are 3L by 4 minus L by 4. This is equal to 0. So this is what is known as. So now in this case, because we have only one unknown constant, so we chose only one subdomain. If suppose there were two unknown constants in the approximate solution, so we would choose one x1 to x2, another maybe x3 to x4 or x2 to x3. No, it can be continuous or they can be discontinuous. So we choose depending on number of subdomains equal to the number of unknown constants. So now if you evaluate this, so this comes out as you will get this as pi up by L cube into ei into a1, and into now if you do this, put the limits. So cos pi x by l and put the limit, so you will get basically yeah, this limit will be x is equal to, so pi by 4 cos pi by 4, so it comes out as basically uh, the limit. So I'm cancelling, so one up minus minus gets cancelled, so this is what you will get, and minus ql by 2 equal to 0. So now if you solve this, so you finally get a1 is equal to q l power 4 upon 2 root 2 ei pi cube. So this becomes no your a1, and therefore the solution is final solution. So you can compare, of course, all the solutions we got. V equal to a1, which is q l power 4 upon 2 root 2 ei pi cube into sine of pi x by l. So this is the final solution. So yeah, this is known as the subdomain calculation. So these are actually the methods of approximate better residual methods for finding out the approximate solution. And you would find that the development of the finite element is also basically based on these methods. Now one thing, now if you look at over here, so this I think still only 16 people are there. Yeah, so now what I was saying is, so I think please ask your other friends also to attend the class. So now the in this what will be discussed based on the bettered residual method or bettered integral method. No, we need to assume an approximate solution which is differentiable up to the highest order derivative present in the differential equation. So, no, we explored the possibility whether we can reduce this differentiability requirement. So, yeah, there is a possibility, and no, we can reduce the differentiability requirement of the approximate solution. And for that, what we do is what is known as weak form. So, I'm going to discuss next is the weak form. So the way we wrote the differential equation itself, or the bettered residual statement or bettered residual integral statement, they are known as strong forms. A strong form means the differentiability requirement is high as per the differential equation, and in the weak form the differentiability requirement is actually reduced. So that is why it is known as weak form, because differentiability requirement is weakened. So it would be lesser. So in the weak form, what we call it, so I have, let me write what I just said. So bettered residual statement requires, we have already discussed that, requires that the approximate solution be differentiable up to the highest order derivative present in the differential equation. So this is yes, and we call this no, the differential equation itself or the bettered residual statement day as it is, and so we call it as, and is known as strong form. And now, so we want to reduce this. So how can we do that? So is we transfer the derivative from the variable to where, weight function w, and that is done through the integration by parts. So we want to reduce the differentiability requirement. So to reduce the differentiability requirement, and the another byproduct of this is that, what we call as the natural boundary conditions, they also get incorporated in the big form itself. So to reduce the differentiability requirement and to incorporate natural, so I will define what are natural and essential boundary conditions. So to incorporate natural boundary conditions, weak form is used. In weak form, what we do in weak form, that or rather we should say to arrive at the weak form. So let me modify this statement. To arrive or to derive, to arrive at the weak form, the derivative from the unknown variable is transferred to weight function w, no, that we have already introduced, weight function w, through integration by parts. So for that purpose we use this integration by parts. So of course you should know this, how we do the integration by parts, or we use the Green's theorem. And that, of course, for the one dimensional problems you can directly do the integration by parts, but for 2D and 3D problems you need to use Green's theorem. So so that you can transfer the derivatives from the variable of interest to the weight function. And when we do the integration by parts, the differentiability requirement is reduced. So we call thus the differentiability requirement of approximate solution is reduced. So that is what we call it as weakened, and that is why the term weak form. So yeah, this is essentially the weak form. Let me take example how we do that, how we arrive at the weak form. So let me take a first example. So first example, I'm basically taking this rod example, so for which we had written the, let us say the weighted residual statement is weight function w into residual. And residual, what we do is, we know, if the differential equation is given, we transfer all the terms to the left hand side, and then whatever we have left hand side, we call that as actually no residual. So the differential equation is d by dx of ea into du by dx. So yeah, this plus q. So this is the differential equation, d by dx a du by dx plus q equal to 0. And when we substitute an approximate solution in this differential equation, we get the residual. So the integral of this dx, actually we are equating it to 0. So this is the weighted residual statement. So this you already know is the weighted. So this term is your RD. This whole thing, this is your RD. So this is weighted residual statement. And in this, when we are substituting an approximate solution, so you see the highest order derivative of u is 2. So it has to be differentiable twice. Whatever polynomial, trigonometric, whatever function we assume, it has to be differentiable twice. So the differentiability requirement on u is no twice. And now what we do, there is no derivative of w, the weight function. So what we want to do is, through the integration by parts, we want to transfer derivative from u to w, so that the differential, the highest order derivative of u is reduced. So in this process, what we can do is we can split now. And now that you see the u term is coming only in the first, so we can split this. We can write integral 0 to L w, and then d by dx of ea into du by dx. That's the first term, plus integral 0 to L w q dx equal to 0. So this is what we have. Now, because we want to reduce the differentiability requirement of u, so we want to transfer this derivative from here to here, and that we do through the integration by parts. So the integration by part, if you use the integration by parts formula, so integration by parts for the first term. So now what we do is, this can be written as the first term. So as you know, the integration by parts formula is first into integral of second term. So the first term is directly w, and the integral of second is, so no, integral d by dx of ea du by dx will be simply ea into du by dx. So because this integral of first term into integral of second, and integral of second would be a into du by dx. So this is what we will get. And then this is a definite integral, so the limit is from 0 to L, minus integration. So integration is 0 to L, the derivative of first function, so that is dw by dx, and integral of the second. So the integral, basically integration 0 to L d by dx a du by dx will be simply a into du by dx. So that will become ea into du by dx. So this is the integration by parts formula we have used over here, and then integral 0 to L, and we have w into q dx is equal to 0. Of course, this term we don't do anything, only for this term we do the integration by parts. So this is what we have got here. And now if you see, the in the integral term, no, the integral 0 to L, you see the highest order derivative of u is now only 1. And of course, the now the highest order derivative weight function w is first. So the differentiability requirement of u has reduced. So now earlier it was in the weighted residual statement, it was second derivative. In the big form, it is the first derivative after integration by parts. So the differentiability requirement of u has reduced, and therefore we call this as big form. Hello, am I audible?
You're audible.
Okay, so have you followed how this integration by parts is used to reduce the differentiability requirement of u? So this is a simple example, and I think, yeah, Abhinav, you are saying that connection is unstable, but I think I am connected continuously, so I don't know why you people are facing problems. Okay, so So this is how we have obtained the weak form. So that is the through the integration by parts. Again, in this process, if you see, there is an additional boundary term. This boundary term means the limit support as 0 to L, so it is integrated. Now this term is integrated at evaluated at x equal to 0, and it is evaluated at x is equal to L. So we call this as a boundary term. From boundary term, we actually identify what are known as primary and secondary variables in the terminology of finite element. And no, we have the terms called primary and secondary variables. So in this weighted residual class of methods, so from boundary term, we identify primary and secondary variables. So what are those? How do we do? So we look at the boundary term. So boundary term, if you see, there are two things. One is the weight function term W is there, and another is this EA into du by dx, other set of terms. So in the boundary term, in place of W, if we write the variable itself, the variable of interest, in this case U, which is the axial displacement of a rod. So whatever we get by substitute, writing variable in place of W, whatever we get, that we call as primary variable. And in solid mechanics problems, these are basically geometric quantities. Like displacement is a geometric quantity. So we know how do we do that. So primary variable, so we get from the weight function term, from weight function term in no in the bound from the boundary term. So now in this case, if you look at in the boundary term, we have only W. So in place of W, we write U. So whatever we get, that is the primary variable. So U is the primary variable, and it's a geometric quantity. And now the another set of variables are known as secondary variables. Secondary variable, so in this case there is only one, so secondary variable, and this is coefficient of weight function term in the boundary term, coefficient of weight function. So in this case, basically now if you look at the boundary term, we have this W, and this is EA into du by dx. So that EA into du by dx is a secondary variable, EA into du by dx, and this is a force. So as you know, du by dx is strain, into Young's modulus is the stress, into cross sectional area is the force. So this is a force quantity. So in solid mechanics, primary variables are basically geometric quantities like displacements, and they could be rotations, and secondary variables are forces and moments. Yeah, any question anybody want to ask?
Sir, can you please repeat the primary variable part? My connection got disconnected, sir.
Okay, so now if you look at this boundary term, I know the boundary term in the weak form. So we have two terms, in the boundary term, it's a product of two terms, W, and the W is the weight function. The other term is A into du by dx. So in place of W, if we whatever form W is appearing, in place of W, we write the variable itself. The variable of interest, unknown variable of interest in this problem is U. So in place of W, if we write no U, so we get U itself. No, if it was dW by dx, then we would have got dW by no du by dx. But in this case, in the boundary term, only W is there. In place of W, we write U, and then whatever we get, that we call as primary variable. So in this case, W is appearing, no derivative, so W replaced by U, and that is your primary variable. And then the secondary variable is coefficient of weight function in the boundary term, which is in this case EA into du by dx. Is that clear?
So what if W is in some other form? not in
So W may be, let's say W may be dW by dx. So in that case, primary variable would become du by dx. But it would be either W or its derivative. That is what would be there in the boundary. So then the primary variables would be either u or du by dx kind of things. So in this case, it's only u. Okay.
yes.
Yeah. So now once we identify primary and secondary variables, so actually when you look at the displacement based finite element formulations, so there what is the importance of these primary and secondary variables? So when we do the finite element formulation, we need to have primary variables as degrees of freedom at the nodes, no, particularly the in nodes or the boundary nodes of the elements. So that is why we worry about what are primary variable and what are secondary variable for a given problem, because to get the accurate, the solution which would converge in the limit when we increase the number of elements, and that would be possible if your primary variables are there as degrees of freedom at the boundary nodes of the element. So that is why we worry about this. And based on the now whether we specify primary or secondary variables at the boundaries, so similarly there is a classification of boundary conditions into essential or geometric and natural or force boundary conditions. So there is a classification of boundary conditions also. So we have what is known as one set of boundary conditions are known as, so whatever boundary conditions are there, they can be written as either they can be classified as either essential or geometric boundary conditions and natural or force boundary conditions. So why geometric is used? Because this is in terms of primary variables, and primary variables are basically geometric quantities. So sometimes they are also referred to as geometric boundary conditions. So essential are geometric boundary conditions. So in this case, prescription of primary variables at the on the boundaries means primary variables are prescribed on the boundaries. Prescription of primary variables at the boundaries. So for the given problem, now this big form we got, we said primary variable is u. So the essential boundary condition would be form u equal to u naught, where u naught is a known quantity. So at x equal to 0, so that could be one possibility. Or you could have u is equal to ul. Ul is a known quantity at x is equal to l. So this form of the boundary conditions are essential boundary condition for the given problem, which is governed by second order differential equation, for which we have written the weighted residual statement and then the big form. So another set of boundary conditions are known as natural or forced boundary condition. So in this case, we basically at the boundaries we prescribe the secondary variables. So as no, the natural boundary conditions are nothing but prescription of secondary variables no, at the boundaries. So now for the given problem, we have already seen the secondary variable is Ea into du by dx. So the natural boundary condition would be of the form Ea into du by dx is equal to, let us say, some q naught, where q naught is a known quantity at x equal to 0, or you could have no, either this or no, either, but the both the ends a into du by dx is prescribed, or at one in no, the primary variable is prescribed, and other in the secondary variable is prescribed, or at both the ends maybe primary variables are prescribed. So all the possibilities are there. I'm just writing typically. So cases. So ei into du by dx is equal to ql at x is equal to l. So this is the form of natural boundary conditions. So you have primary and secondary variable, and there are corresponding essential and natural boundary condition in a given problem. So any given problem, we can say whether what are the, based on the differential equation, then we write the weight weighted residual statement, get the big form, then we can identify the primary and secondary variable, and then we can classify the given boundary conditions either as no essential boundary conditions or natural boundary conditions. So these are all things we look at in the basically this big form. So let me take another example. So right now I'm going taking basically the differential equations. So let me now take the second example. So we have also worked, looked at the beam problem. So the beam problem is, now the boundary condition, of course, in general can be anything. So see, this is x, and we said that this is y. The deflection along y is v, and the distributed load is we had said it is. So this is a beam problem. The subjected to distributed force q. Q is a distributed force, and let us say L is the length, and EI is the flexural rigidity, Young's modulus into cross sectional area. So now you have, for this problem you already know that the governing differential equation, governing differential equation. So I have not derived this differential equation, but I'm making use of this. So as of now, you have to know that if you are given a differential equation, how to write the better residual statement, how to write the big form. So that is what I expect you to do this from this. So d by dx square, and then you have ei into d2v by dx square minus q equal to 0. So this is the differential equation, the deflection of this beam, and this is based on Euler-Bernoulli beam theory. So the deflection is basically governed by this differential equation. So for the timing, now you have to learn as if the differential equation is given, then how to get the big form. So first we write what is known as the weighted residual statement. So now this is the differential equation. All the terms are already there on the left hand side. So whatever we have now, when we will be substituting approximate solution in this, so whatever we get, we call that as the domain residual. So we integrate, multiply that domain residual with w and integrate it from basically 0 to L and equate it to 0. That is known as weighted residual statement. So that RD is going to be d2 by dx square ei d2v by dx square minus q dx is equal to 0. So this is the weighted residual statement. Out of this, this is your RD, domain residual, and this is you already know the weight function. So this is the weighted residual statement. And now what we want is, if you look at here, now in this particular term, the highest order derivative of v is fourth derivative, because d2 by dx square here and d2v by dx square is already there. So highest order derivative of v is fourth derivative, w no derivative. So what we want to do is we want to transfer the derivative from v to w, so that the differentiability requirement of v, approximate solution v, is actually reduced. So now we write this one by let me split the two terms the here. So we have integral 0 to L w, and then you have d2 by dx square ei into d2v by dx square dx. That's the first term, minus integral 0 to L w q dx is equal to 0. That's the second term. And now we do the integration. Now what we want actually here is, we want to transfer the derivative from v to w, so that the differentiability requirement of v is reduced. And not only that, we want to, if possible, we want to make the derivatives equal in v and w, the variable of interest and the weight function v. So in this case, highest order derivative v is fourth derivative. So we want to transfer the derivative to w, so that w also becomes second derivative in the integral, and in the integral we have second derivative of v. So we want to equally distribute the derivative between v and w through the integration by parts, and the final resulting expression we call as weak form. So now what we do is integration by parts once for first term. So integration by parts of first term. So we do it only once. So let me first write that what we get. So from this we will get now when this we treat as the first term, and this whole thing we treat as the second term. So now if you see in the integration by parts formula, first into integral of second. So first function is w, and the integral of second. So it is no, if you look at the integral of d2 by dx square ei d2v by dx square dx. So one derivative will be going out through the integration process, because integration is inverse of differentiation. So one differentiation will go. So we will get d by dx of ei into d2v by dx square. So this is what we'll get. And this is a whole no the first term in the integration by parts formula. So we put the limits 0 to L, and then minus integration 0 to L, the derivative of first term, so dw by dx, and integral of second term, so the integral will become one derivative would reduce, so ei d2v by dx square dx. So this is going to be the another second term, and of course the last one remains same, integral 0 to L w q dx is equal to 0. Now we do the integration by parts once again for this integral term. Of course this is the boundary term, we don't do anything over here. No, we don't do any, this is already the boundary term, there's no further integration anything on this. But if you look at this integral term, which is integral 0 to L dw by dx d by dx of ei d2v by dx square dx. So in this still you see the highest order derivative of v is third derivative, and highest order derivative of weight function w is only first. So we can do the integration by parts once again and transfer the derivative from v to w, so that the derivatives of v and w are equal. So we want to equally distribute the derivatives between v and w. So we do the integration by parts once again. Integration by parts once again. So another first term of course remains as it is, the boundary term. So w d by dx of ei into d2v by dx square. So this term remains as it is, limits 0 to L. Now again we want to use the integration by parts formula. So now if you see, this is the first function, this is the second function. So first function into integral of second, minus sign is already there, so it will be there. So first function is now dw by dx, and integral of second. So because it is integral, when you do the integration of this term, so integral and then d by dx ei d2v by dx square dx. So the derivative will go. So we will get ei d2v by dx square, and of course evaluated at 0 and L at the boundary. So that's the first term when we do the integration by parts for this one, and minus minus plus integral 0 to L derivative of the first function. First function is already dw by dx, its derivative will become d2w by dx square, and integral of second, so the differential will go. So we will have ei d2v by dx square and then dx, and the last term of course is minus integral 0 to L w q dx is equal to 0. So this is what we get if we do the integration by parts twice. So now if you see in the integral term, although in the boundary term you will have, so we can't do anything with the boundary. boundary term, no, the first boundary term you see no derivative of w, third derivative of v. In the second boundary term, first derivative of w and second derivative of v, so those will remain there. But if you look at this integral term, this particular term, in this now you see the derivatives of v and w are same, so we have equally distributed the derivatives between v and w. And now the differentiability requirement of v is reduced to, in the as per the better residual statement, the v approximate solution for v should be differentiable at 4 times. But now in the b, as per the b form, the highest order derivative v is say only second derivative. So when we assume an approximate solution, it should be differentiable only twice. So the differentiability requirement of approximate solution for v is reduced. So this is what we call as weak form. So this is the weak form of the original differential equation. And now again, I know we look at how do we identify the primary and secondary variables. So now again, let's look at that. So primary variables. Now primary variables are identified from the boundary terms. So in the first boundary term, you have this w, and so in place of w, now the unknown variable of problem is v here, the transverse deflection of the beam. So in place of w we write v, whatever we get, that is the primary variable. So in the first one only w is there, in place of w we write v, so we get v. And in the second boundary term we have dw by dx, so in place of w we write v, we get dv by dx. So the second primary variable is dv by dx. So as you know, v is the deflection of the beam and dv by dx is the slope of the beam, rotation of the beam. Both of them are geometric quantities. Deflection is geometric quantity and the rotation or slope is also geometric quantity. So primary variables are basically geometric quantities. So first the first primary variable is coming from the first boundary term. The second primary variable is coming from the second boundary term. That is, in place of w we write v, so we get dv by dx in the second boundary term. So similarly, we identify the secondary variables. So secondary variables are basically the coefficients of weight functions in the boundary terms. So in the first one we have actually this. So the secondary variable is, of course, the secondary variable interpretation is in terms of shear force. So I am putting a minus sign, although if you write also without minus sign, that's also a correct identification of basically the secondary variable ei d2v by dx square. So here you have this d by dx ei d2v by dx square. So that's the secondary variable actually corresponding to v. And similarly, in the second term, the coefficient of weight function term is ei dv by dx square. So that is the second primary variable, dv by dx square. And that's the secondary variable corresponding to dv by dx. Because why they are known as corresponding or conjugate primary and secondary variable, because this is shear force and this is the deflection. Product of these two will give you the work done. Similarly, this is the slope or rotation and this is the moment actually. Ei d2v by dx square is actually bending moment. So the bending moment into slope will give you again work done. So they are the corresponding, there is a correspondence between the primary and secondary variable. So corresponding to primary variable v, the secondary variable is minus d by dx ci into d2v by dx square, and corresponding to primary variable dv by dx, the secondary variable is ei into dv by dx square. This is shear force and this is bending moment. So yeah, this is about the identification of primary and secondary variables for this problem. And sometimes if you look at some problems, maybe you would have more than in this case we have two boundary terms. Let's say we have three boundary terms, and in the third boundary term also, instead of w derivative only w is coming. So when you identify, the primary variable would be corresponding to w and the secondary variables have to be combined over there. So that you should keep in mind when you identify the primary and secondary variable. If there are multiple terms involving the same form of weight function in each boundary term. So now once we identify primary and secondary variables, Then we talk of again the form of essential boundary conditions and natural boundary conditions. So essential boundary conditions. So essential boundary conditions would be the prescription of basically primary variables. So one possibility, these I am writing all possible forms of the essential boundary condition. So because primary variables are v and dv by dx, so their prescription at the boundaries form the essential boundary condition. So either v equal to v naught. V naught is a known quantity. It could be 0 or non-zero. At x equal to 0, so that is 1. Or we have no I of course v and dv by dx both can be prescribed at a boundary. So dv by dx, so this can be and or r, both possibilities are there. So r dv by dx is equal to some theta naught. Theta naught is a known quantity at x equal to 0. So other is v equal to vl. Vl is a known quantity at x is equal to l. R dv by dx is equal to theta l. Theta is a known quantity at x is equal to l. So this will be the form of your essential boundary condition. So any boundary condition which is in which the primary variable either v or dv by dx are prescribed would be referred to as essential boundary condition. Then we have natural boundary condition. Natural boundary conditions will be the prescription of secondary variables. So you could have one secondary variable is minus d by dx of ei into d2v by dx square is equal to say some v naught at x equal to 0, or we will have this ei d2v by dx square is equal to m naught. So here this is capital V, which is shear force. So now that you have to keep in mind. And v naught is a known quantity, could be 0 or non-zero. M naught is a known quantity, could be 0 or non-zero at x equal to 0. So this is one. So where at x equal to 0 these quantities are prescribed, they could be prescribed at x is equal to L also. So minus d by dx of ei d2v by dx square is equal to vl at x is equal to L, or no, you could have ei into d2v by dx square is equal to ml at x is equal to L. So these are the no natural boundary conditions. Now let me take some examples, and no on a particular at a particular boundary you can either prescribe the primary variable or corresponding secondary variable. You cannot prescribe both of them simultaneously. So that's how no when you use packages or anything, so when you prescribe the boundary condition you will have to keep in mind that what boundary condition is to be given, either no you prescribe the primary or secondary variable. So let me take some examples. Let us say no in terms of only boundary condition. So let us say we have a cantilever beam, and cantilever beam is of course same no the load q is there. Of course any load will be there. Right now I'm only talking about the boundary condition. So this is x and this is y coordinate. The deflection is v in this direction. So as you know, at x equal to 0, because fixed beam, so v will be 0, no deflection allowed, and also dv by dx would be equal to 0. So these are the now both the boundary conditions are at x equal to 0, v equal to 0, and dv by dx equal to 0. For this problem, v and dv by dx both of them are primary variables. So these are the essential boundary condition. And at this end, the shear force and bending moment is 0. So we will have minus d by dx of shear force is 0 and bending moment is 0. So minus d by dx of ei into d2v by dx square. This is equal to 0 and no shear force at the right end, and ei into d2v by dx square equal to 0, no bending moment at x is equal to L. So both these are, so these are the essential boundary conditions, and these both are natural boundary condition, NBCs, natural boundary conditions. So this is one no say, classification of boundary condition. Now suppose we talk of let us say a simply supported beam. This beam again know the same loading q is there, this is x, this is y, and the transverse deflection is g. So you know this for this what are the boundary condition. So one is that the beams have this is not allowed to move along y direction, so b equal to 0. That is one. The second is now the bending see because there is going to be reaction here, so the shear force would be non-zero and an unknown, so we do not know a priori what is shear force over here, so that's an unknown, but we know that bending moment is 0. The beam is free to rotate here, so no moment. That means ei into d2v by dx square is equal to 0. So these are the boundary conditions on the left side at x equal to 0, and similarly here v equal to 0 and ei into d2v by dx square is equal to 0. So in this, if you look at this, is the essential boundary condition, this is also essential boundary condition, and this is natural boundary condition because the secondary variable ei into d2v by dx square is prescribed. This is natural boundary condition. So no, like that, no, you can, so you will see either no v is prescribed or dv no the shear force is prescribed. So v are d by dx of ei into d2v by dx square is prescribed, dv by dx is prescribed, or corresponding ei into d2v by dx square is prescribed. So from each set, no, at each end from each set you will have one primary variable prescribed, one secondary variable, or both primary variable or both secondary variable, depending on the boundary condition. So like that, no, for the other cases also you can classify the boundary conditions over here. Hello, are there any questions, doubts so far whatever we have discussed? So we have just discussed what are how to write the weak form, how to identify primary and secondary variables, and then what would be the form of essential boundary conditions and what would be the form of natural boundary conditions. So this is what we have discussed so far. So now let me now introduce the approximate analytical solution based on weak form. So far now the five methods I discussed: Galerkin, Petro-Galerkin, least square, point collocation, subdomain collocation. So those were based directly on the bettered residual statement. Now since we have developed the weak form, so we can also arrive at the basically the approximate analytical solutions of differential equations based on the weak form. So essentially the steps are more or less the same what we discussed based on the bettered residual statement, but only thing is when we assume an approximate solution, now that has to be differentiable as per the weak form rather than the strong form of the better or the bettered residual statement. Another thing is earlier we said that we assume an approximate solution, and then before we substitute that in the differential equation, we eliminate some of the constants by satisfying all the boundary conditions. In the weak form based solution, no, we say that basically eliminate the constants only by satisfying the essential or geometric boundary conditions. So that is the difference when we talk of analytical solution based on weak form. And see why I'm discussing this, because these form the basis for development of no finite elements, and that is why I'm discussing this. I think if you say that you have done a course on finite elements, so it is essential that you know these concepts, and that is why I'm discussing this. So next is approximate solution based on weak form. Of course, no, there can be many other examples to develop the weak forms itself. So the approximate solution based on weak form. So now the here only difference, as I said, it is similar to what we have already discussed, what are the steps to obtain the approximate analytical solution. So those steps are near, no, more or less the same, except that I already stated. So let me write the same thing what I have just stated. That no, the difference is that assumed solution should be at least differentiable up to the highest order derivative present in the big form. Earlier it was in the differential equation itself for the weighted residual statement, a weighted integral statement. But here we say assumed solutions should be at least differentiable up to the highest order derivative, up to the highest order derivative present in the big form, present in the big form. So not in the boundary term. We are not saying, no, when we say in the big form, basically in the integral terms, not in the boundary terms, and should satisfy essential boundary conditions, and should satisfy essential. Now we have defined what are essential boundary conditions. So essential boundary conditions. So this is the only difference compared to what we have already done. So now suppose we want to take some examples on this. So let me again the approximate solution. I am again hindering, basically taking only roaming around these two examples, so that we appreciate the different ways of solving the same differential equations. So now example one, I am taking the same, this d by dx of ea into du by dx plus q equal to 0. So this is the differential equation, and physically the problem is that this rod, and one end of the rod is fixed, and this is subjected to a uniformly distributed force q. Length of the rod is l, and product of Young's modulus and cross sectional area ea and q are constant along the length, and this origin of x is here, the displacement u is measured along x direction. So here this eaq, these are constant along length, constant along x. The boundary conditions for this problem, as you know, boundary conditions are u equal to 0 at x equal to 0. So as you now know, this is the essential boundary condition, because for this problem we have already seen that u is a primary variable, and the second, so this is the first boundary condition, and the second boundary condition is that du by dx equal to 0 at x is equal to l. That is the natural boundary condition. Now for this problem we have already derived the weak form, so you know that weak form. So weak form was w ea du by dx, whole thing evaluated at 0 and l, minus integral 0 to l dw by dx into ea into du by dx. This we have already derived just now, integral wq dx equal to 0. So this is a weak form. Now how we want to, so the first step is to assume an approximate solution. But now see, earlier if you remember, in the weighted residual statement based approach, we had assumed a solution which was to be differentiable at least twice, because highest order derivative of u was 2. But now in the weak form, in the integral term, you see the highest order derivative of u is first derivative. So whatever we assume, it should be differentiable at least once. So we assume an approximate solution which is a now let me take a polynomial, although it can be anything. So the approximate solution should be differentiable only once. So minimum I can do is I can take a0 plus a1x. So that's the minimum thing. Of course I can keep on adding the terms for improving the accuracy. So and now this no u is a0 plus a1x, du by dx would be equal to a1, which is non-zero existing. So it satisfies the requirement that it should be differentiable up to the highest order derivative present in the weak form. So then before we move further, we use the essential boundary condition and eliminate another one of the constant here. So essential boundary condition is u equal to 0 at x equal to 0. So this implies no, yeah, no, on the right hand side here, if we put x equal to 0, we get a naught, and that is equal to 0. So if a naught equal to 0, then means finally we have the solution as u equal to a1 into x. So we are taking a linear solution, linear in x. And now we want to find out this a1. How do we want to find out this a1? So, we want to find out a1 so as to satisfy the weak form. And now if we want to satisfy the weak form, we will have to choose the weight function as we did earlier. So let us use the Galerkin method. As per the Galerkin method, of course, in the weak form based approach, we will not use say this no least square method or point calculation or subdomain calculation or calculation. What we can do is either the Galerkin or the Petro-Galerkin. Most commonly used method is Galerkin method. So in the Galerkin method, we will take basically weight function w is equal to no the you remember in Galerkin method the weight function w will be what? Can anybody tell what would be the weight function w now for this problem? Yes, please. What would be weight function w in we are using Galerkin method? Hello, am I audible? Yes. Galerkin method, how do we choose the weight function? So we look at the approximate solution after satisfying the boundary condition. In this case, we are only satisfying the yeah, x, right. So right, thank you, it's rightly said. Weight function w would be x, because now this is our approximate solution. In the Galerkin method, weight function is chosen as the coefficient of unknown constant in the approximate solution after satisfying the boundary condition. In this case, we need to satisfy only the essential boundary condition, so we have already done that. So the weight function w is going to be actually x in this case. Now we want to substitute this in the weak form. So this is your weak form. So we substitute in the weak form. This a boundary term has got two parts actually. So the boundary term can be written into two parts, w ea into du by dx at x is equal to L, minus we will have W EA du by dx at x equal to 0. So these are the two things we will get from the boundary term. And then minus we have integral 0 to L, of course that is same, dw by dx into EA into du by dx plus integral 0 to L wq dx equal to 0. So this is weak form. Now let's put the values. So our w is equal to x actually. And so this is this quantity is a boundary term evaluated at x is equal to L. Now from the boundary condition, now you see the here du by dx is appearing, which is the secondary variable of the problem. So it is already prescribed at x equal to L. So if you look at x is equal to L, w is non-zero. W will be of course equal to L at x is equal to L. But as far as du by dx is concerned, du by dx is 0 at x is equal to L in the given problem. So the first term will become overall 0. Now the second term, if you look at w ea into du by dx, so this ea into du by dx at x equal to 0 is not known, but w actually is equal to x, and w equal to x, and at x equal to 0 we put no, so then w will become 0. So this term will also become 0. Then we have minus integral 0 to L dw by dx, derivative of w with respect to x will become 1, and then you have ea, and then du by dx. So this is your u, its du by dx is simply going to be a1. So we will have a1 dx plus integral 0 to L w is x, so q dx equal to 0. So now if you see, the integral of the first term is simply minus ea L into a1, so that is what we will get. and the second term plus no x square by 2, put the limit, so ql square by 2 is equal to 0. So now it's a straightforward. So you will see that we will get a1 here as ql upon 2ea. So therefore finally the approximate solution, this is an approximate solution, so approximate solution u is equal to ql upon 2ea into x. So you see the exact solution we have discussed in the earlier class. That exact solution for this problem based on the weighted residual statement with the quadratic solution. Actually, no, the is quadratic, but we are assuming it's a linear solution. So now if you evaluate u at x is equal to L, so you will find that will become QL square upon 2EA, and you will find that this is, although this is a linear solution, the exact solution is quadratic function of x, but this linear solution gives accurate value of u at x is equal to L from the exact solution we got earlier. If in that, if you put x is equal to L, so that is value of u at x is equal to L, you will get exactly the same thing, QL square upon 2a. So even a linear solution is able to give you no accurate solution at x is equal to L. Of course at other locations it won't be correct, and when you calculate the stress, it would be correct at the center of the rod, that is e into du by dx. So you will get it as basically ql upon 2a, and that would be the stress at center, but other places it will not be correct, but you are able to get at least the solution in a much simpler way. Now the, of course, the working out of this entire solution based on this linear polynomial, that was a minimum requirement. But you can also take the solution with more number of terms, and if you do that, you will of course get the more accurate solution. So for example, no accurate solution, and it will turn out to be exact solution, because we know that for this problem the exact solution is quadratic function of x. So now the same problem, let me demonstrate if we use three term solution. So just now I took two term solution, that is in the approximate solution initially we assumed basically two terms. So now let me take u equal to a0 plus a1x. This a0 plus a1x is the minimum we can, we can start with, but we can add more number of terms. So let's say we add a2 x square in this. So before we proceed further, first what we do is we eliminate some of the constants by satisfying the essential boundary condition. So we are continuing the same problem. So for this we know essential boundary condition is u equal to 0 at x equal to 0. So we do that. So this side, no, right hand side, if we put x equal to 0, we simply get a naught, and that is equal to 0. So then what you have is resulting approximate solution is simply a1x plus a2x square. This satisfies the essential boundary condition, that is u equal to 0 at x equal to 0. So now this is the solution, and now if you look at, of course, the derivative of this is du by dx is going to be a1 plus 2a2 into x. So that is what will be du by dx. Now see, there are two unknown constants in this approximate solution, a1 and a2. So we need two equations. How do we get those two equations? So that is by choosing two weight functions. How do we choose those weight functions? In Galerkin method, one weight function will be coefficient of a1, that is x. Another weight function would be coefficient of a2, that is x square. So we will have now, we have to set up two equations to find out a1 and a2. For that we need two weight functions, and in the Galerkin method the two weight functions are two weight functions. One is say w1, so w1 is say the coefficient of a1, which is x, and the second weight function is, let's say, w2, which is the coefficient of a2, that is x square. And this is as per the Galerkin method, because in the Galerkin method we take the weight functions as the coefficient of unknown constants in the approximate solution. So now we will have to generate two set of the equations. So one is by taking w equal to w1, that is x. Another equation by taking w equal to w2, that is x square. So again, if you look at as far as the boundary terms are concerned, so they are going to be 0 for both cases when w1 equal to x and w2 equal to x square, because at x is equal to L, du by dx is 0. So there the boundary term will become 0, and at x is equal to 0, w1 and w2 they are equal to 0. So one equation we take from the w1. So we basically write the equation as w1 into ea into du by dx at x is equal to L minus let me first write the boundary terms, minus w1 ea into du by dx at x equal to 0. So this boundary term minus integral 0 to L w1 d w1 by dx into ea into du by dx. This is a big form, I'm just writing the same big, plus integral 0 to L w1 q dx. Only thing, in place of w we are writing w1. Now if we put the values, so as I said, at x is equal to L, du by dx is 0, so this whole thing term goes to 0, minus at x equal to 0, this is 0 because w1 is equal to x, and at x equal to 0 that is going to be 0, so that is also 0, minus integral 0 to L. Now dw1 by dx is going to be 1 because the w1 is equal to x into ea, and then du by dx is a1 plus 2a2 x. Now this is a function of x, of course. Dx minus integral no, plus integral 0 to L w1 is x q dx equal to 0. So now if you do the no the integration by parts, no sorry, not the integration by parts, you just carry out the integration. So if you do the integration, the first term will become minus e a l into a1, and plus you will get e a l square into a2 plus ql square by 2. So this is one equation equal to 0. This is one equation. Now another equation we get from the taking w is equal to w2, because now there are two unknown constants, so we need two weight functions. So now the second equation we will get from w2. So we will have w2 now ea du by dx at x is equal to L minus w2 ea du by dx at x equal to 0 minus integral 0 to L dw2 by dx into ea into du by dx plus integral 0 to L w2 q dx equal to 0. So now again now if we put the values, so no, at x equal to L this is 0, so this term goes to 0. At x is equal to 0, w2 will be 0, so minus again 0 minus integral 0 to L, and now w2 is x square, so d2 now this is going to be basically, if you look at the no the second term, so you will have this d2w by dx as 2x, and then ea, and then du by dx is of course a1 plus 2 a2x dx, so that is plus integral 0 to L x square q dx equal to 0. So now in this, if you do the integration, you get the second equation, and that equation would be minus you will have ea L square into a1 plus you will get, no, that's the straightforward integration, so 4 ea L cube upon 3 into a2 plus ql cube by 3 equal to 0. So this, let's say, equation number 2. Now if you look at no, we can simplify these equations. So equation 1 and 2 be used to solve no, a for a1 and a2. So no, the whole thing, now if you look at equation 1, what I have written here, the whole thing, if you divide it by eal, and the unknowns you keep on one side and the known quantities on the other side, so equation 1 can be written as a1 plus a2 into L is equal to ql upon 2 ea. And similarly, if you look at the equation 2 just now I have written, so you divide it whole thing by no eal square and take unknowns on the left hand side and known quantities on the right hand side, so you'll get a1 plus 4 upon 3 into a2l is equal to ql upon 3ea. So now these two equations can be solved for a1 and a2. So if you solve for a1 and a2, you will get from this, it's a straightforward, no, you can subtract no the this from no this equation, then get a2 directly, and then from any one equation you can get a1. So you will get basically no, A1 is equal to QL upon EA, and no, the A2 will be equal to this minus Q upon 2EA. So that is what you will get as values of A1 and A2. And once you have got the values of A1 and A2, so then finally, the solution is, the final solution of the problem is U is equal to, first is A1, which is QL upon EA into X, and minus second is A2, which is minus Q upon EA, so QX square upon 2EA. So this is the solution. You will find, of course, that now we have taken the quadratic term in the approximate solution, initially assumed approximate solution. So this is same as, of course, the exact solution. So from this big form based Galerkin method also, we are getting the essentially, the same solution. So this is, I think, yeah, I want to stop here. And if you have any doubts and questions, you can ask, and I will continue. So one is that, no, I want to take class on Saturday, as I had informed you through the email. So this coming Saturday, I think the timing I will keep same, 9:30 to 11. And of course, the next week classes will be as usual on Monday and Thursday. So only thing is, because the last Monday I had to go somewhere, so I could not take that class. So in place of that, I'm going to take the class on Saturday. Tomorrow, of course, is a holiday, I think. So I will take the class on Saturday, 9:30 to 11. So I request you, all of you, to please join class on Saturday also. So now, any questions and doubts? Yes, please. Anybody? Any question? Yeah. Yes. Yes. Please say again.
Sir, I think we have our classes of Friday schedule will be there on Saturday. So we have classes from 9 to 12. Sir.
On Saturday.
Yes, sir.
Is Saturday is Saturday working as per Friday timetable?
Yes, sir.
Oh. So then I think, in that case I will take class on next Saturday, no, next to next Saturday. So then I will not take a class on 15th in that case, but I will take class on 22nd. So then the next class would be on 17th, and then on 20th, and then on 22nd. I think 22nd then I should be able to take. Okay, then in that case, next class would be only on Monday, and extra another class in place of this last Monday will be on 22nd January. Yeah. Any other questions and doubts? Whatever I have discussed so far. Okay, so if there are no questions and doubts, I am stopping here. Thank you all for your attention. I request you all again to please go through this, because I am uploading the PDF of this whatever I am writing in the school, this Impartus under backpack, and the videos of the lectures are also available under lectures. So you should watch and make sure that you understand. I think, and by next week I will also give you assignment, and which would be based on all these concepts whatever we are discussing, and you all have to submit that. So please make sure that you understand all these concepts. So go through the lecture videos and these PDFs, and make sure that you understand all the things. Okay, thank you all for your attention.